right, so probability recap number 2 is going to go over compound events. Now, compound events is the probability of multiple outcomes coming true. Hence, you're compounding two things or more, 3, 4, ever many as you want. Okay, so there are two types, though, of compound probability. There's the first one, which is the independent events. And independent events, that's where the outcome of the first event does not affect the second event, or the second event will not affect the third event, like rolling a dice. Rolling a dice is only going to, you have 1/6 chance of getting a 1, right? When you pick up that dice and you roll it again, those odds, theoretically, stay the same, 1/6 every single time. If you take something out of a bag and then you replace it, your odds don't change. You take a card out of a deck and then you put it back in the deck, your odds will not change the second time around. These are called independent events, okay? Now, the word event is making a choice with probability. So it's anything, it's the spin of a dice, it's the flip of a coin, it's choosing a card, it's an event. It's something that you're choosing, right? Remember, independent events, first outcome does not affect the second outcome, and so on. And like I said, example of this, right? What is the probability of rolling a standard dice twice and getting an even number, then a 5? Well, your chances of getting an even number is 1/2. Your chances of then getting a 5 is 1/6. And to figure out how you find the compound probability, you multiply those two fractions and you get 1/12. And that's the independent probability of you having those two things happen, right? So it's like flipping a coin 3 times. 1/2 times 1/2 times 1/2. You have a 1/8 chance, and it is an independent, meaning one does not affect the other. However, we also have things called dependent events. Dependent events, this is where one event does affect the second one. This would be like taking a card out of the deck and not replacing it and then picking another card. Well, guess what? Now there's 51 cards, not 52, so your odds change there. And if you took one ace, you now have 3 out of 51, not 4 out of 52. So odds will change depending on the first event, okay? So this right here, we'll give an example of this right here. There's a bag of 3 green, 6 yellow, 4 red, and 12 blue markers, okay? A marker is drawn and the keyword not replaced, right? If we replace it, it's independent, meaning it won't change the probability. But since we're not replacing it, the second item is going to have a different probability. So picking red, right? There's 4 red out of, there's 10, 13, 25. So 4 out of 25. That's the probability of getting red. But since we're not replacing it, when I then decide to select the blue, there's now only 24 cards left, or 24 markers, and there are still, though, 12 blues. So you can see how the probability changes. Now, obviously, you multiply those two fractions, simplify. So if you were going to do both yellow, your yellow chances are 6 out of 25. But the second time, sorry, we're doing blue, both blue. So blue is 12 out of 25. And assuming that I get blue, hence that's what this is about, getting blue 2 times in a row, I now have 11 blues and 24 total markers left. Okay, and then you'd multiply those out. So you can see here, dependent, the first outcome will affect the second one. Okay. Now, there's also something called the counting principle. The counting principle, that is a way to find the total amount of outcomes, right? We discussed this earlier about Sonic, right? Sonic has a billion different things you can choose from. All you got to do is take, okay, small times the flavors, times the fruits, times whatever other flavors, multiply all those things together, and that's your total outcomes, okay? So, basically, if one activity can occur, let's say, 2 ways, and another activity can occur in 3 ways, then both activities can occur in 6 ways. You're just multiplying, right? 2 times 3, that means there's 6 total outcomes, okay? So, way to figure out how many outcomes, it's like, okay, to leave her office, Karen can choose between 3 sets of stairs and 7 doors. Well, that's just going to be 3 times 7 equals 21. Pretty simple. So that's how you find out total amount of outcomes, right? Like here, a dinner menu consists of 5 appetizers. So you have 5 choices there, 12 entrees, and 3 desserts. 5 times 12 is 60. 60 times 3 equals 180. So there you go. That's how you find out, we call that the counting principle, and that's how you figure out how many different outcomes there can be. Now, tree diagrams is the same thing essentially, except you're going to draw this so that we can see it. Now, this is used, like I said, in algorithms for creating video games and different things. But on the small, like what we're going to do, make small ones, it tells you every specific outcome, right? It's kind of like, hey, I can figure out real simply how many outcomes there are. There's 180. That's not going to tell me every single outcome. Like, I don't know every outcome. I would have to actually test that, right? We're not going to do that often, but when we do, we use tree diagrams. So an example of this is the spinner below is spun twice. Okay, event 1, I could get A, I could get B, or I could get C, right? Boom, I could get those 3 options. Event 2 is going to tell me that, well, if I got A and I spin it again, I still have a chance of A, B, or C, right? If I got B and I spin it again, I still have a chance of A, B, or C. C still has a chance of A, B, or C. And all of these are your total outcomes. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And we could have figured that out from the get-go, right? Because we could have just said, hey, there's 3 choices, and we're going to do it twice, so 3 times 3 is 9. We could have figured out that pretty simple. But I wanted to know specific outcomes, which in this case means that, hey, I want to figure out each outcome. Well, I could have AA. That's my sample space. A, right? Then I could have had A, B, and I could have had A, C. 3 outcomes, there's my specific outcome. And then I would do that again until I have 9 specific outcomes. And what that does is it helps us find the probability of specific things happening, okay? And you would only use this for something small like this. You wouldn't use this for something large unless you had software like video game algorithms. So let's do one more though. The popcorn stand offers buttered or unbuttered. That's 2 choices. So event 1, I'm gonna have buttered or unbuttered. And then I can choose small, medium, or large. So I could get buttered and I could get small. I could get medium and I could get large. Same thing if I got unbuttered. Small, medium, and large, right? That's 2 options times 3 options, which is 6. And there we go. You'll see BS, BM, BL, US, UM, and UL. 6 outcomes.